Every time you click a link, that click doesn't travel straight to the network. It falls through 7 invisible floors first, a structure engineers call the OSI model. Floor 7 is application, the part you actually see and touch, your browser, your app, your click. Floor 6 formats and sometimes encrypts it. Floor 5 keeps the conversation straight, so it never gets mixed up with any other. Floor 4 slices it into numbered pieces. Floor 3 addresses it for the whole internet. Floor 2 addresses it for the next hop. And Floor 1 turns all of it into real, physical signals. Slow motion, watch one click fall through all 7 in order. Slow motion, take 1, you click a link. At layer 7, application, your browser decides what it wants. Fetch this page, plain, human-shaped intent. That intent drops to layer 6, presentation, which translates it into a common format both ends agree on, and, on the modern web, encrypts it before it goes any further. Layer 5, session, opens a conversation and tracks it. A quiet bookkeeper making sure this exchange doesn't get tangled with the dozen others your device is also running. Layer 4, transport, slices the conversation into numbered segments and makes a choice. TCP's careful, check delivery, or UDP's faster, no guarantees speed. Layer 3, network, stamps each segment with a source and destination IP address, the addressing that lets it cross the entire internet, not just one room. Layer 2, data link, wraps it again with hardware MAC addresses, valid for exactly one hop, rewritten at every router along the way. Layer 1, physical, turns the entire stacked package into something a wire, a fiber, or the air itself can actually carry. Electrical pulses, light, or radio waves. Notice what happened. Nothing got rewritten, only wrapped. Each layer adds its own small envelope around the layer above, like nested packaging. That's called encapsulation, and it's why layers can change independently, swap Wi-Fi for Ethernet at layer 2, and layers 3 through 7 never notice. On the receiving end, a server does the exact same climb in reverse. Unwrap the physical signal, read the MAC, read the IP, reassemble the segments, restore the session, decode the format, and finally hand a clean request to its own application layer. All 14 floors, 7 down, 7 back up, usually finish before you'd notice a single frame of lag. The fine print, generations of students memorize the order with a mnemonic. All people seem to need data processing, 1 word per layer, top to bottom. The real internet doesn't strictly enforce 7 separate boxes. Protocols like TCP/IP compress this into 4 practical layers. OSI is the teaching model, TCP/IP is the working one. Real protocols map onto real layers. HTTP and TLS live around layer 6-7, TCP and UDP are layer 4, IP is layer 3, and Ethernet or Wi-Fi handle layer 2. Why keep the layers separate at all? So one team can rebuild Wi-Fi hardware while another rebuilds encryption, and neither has to understand the other's job. It's also the first thing network engineers reach for when troubleshooting. Is this a layer 1 problem, a bad cable, or a layer 7 problem, a broken app? The model sorts the search. And it's older than the modern internet itself, standardized in 1984, designed for a world of competing network vendors who needed one shared vocabulary. Format, track, slice, route, address, transmit, 7 jobs, 7 floors, wrapped layer over layer, unwrapped in reverse on the other end. Every click you've ever made climbed this exact staircase. Thanks for watching. Next time an engineer says that's a layer 3 issue, you'll know exactly which floor they mean. Follow how it all runs for more. See you in the next one.